the first half of the year 1812, Mount Tambora began to rumble. The immense mountain had towered mutely over the Indonesian archipelago for centuries, an entire culture growing and prospering at its base, with trading links as far as Cambodia and Vietnam. Nearly 2,000 miles away on the distant island of Sumatra, Sir Stamford Raffles, the future founder of Singapore, was stationed. On the 5th of April 1815, he reported the sounds of distant gunshots, and troops were moved to counter the supposed military threat. He struggled to sleep that night, the mysterious cannons still echoing in the distance and keeping him from his slumber. The next day, however, the true cause of the blasts was revealed. A thin layer of ash began to descend from the darkening skies. Over the next few days, the heavens blackened further still, and the atmosphere became stuffy and close, as if before a great storm. And on the evening of the 10th of April 1815, 1,600 miles away, Mount Tambora exploded. This was an eruption, the likes of which had never before been seen by human eyes, nor has ever been seen since. The mountain became a flowing mass of liquid fire, with columns of flame reaching high into the air. As the core of the volcano collapsed, it blew itself apart. Semi-molten volcanic bombs the size of coconuts rained from the heavens. Scorching, racing pyroclastic flows cascaded down the mountainside, wiping the village of Tambora off the map. 10,000 people were killed and another 35,000 left homeless. The entire culture and language of the Tambora people was erased in days. The eruption tore the top off the mountain overnight. When the sun rose, Mount Tambora was 1.5 kilometers shorter than the day before, with a caldera more than 6 kilometers across. But the sun didn't shine over Indonesia that day, or for many days after. Stamford Raffles reported taking his breakfast by candlelight, the volcano disgorging 100 cubic kilometers of rock and ash, which filled the air and darkened the skies. And as ash and noxious gases lofted high into the atmosphere, they were spread around the globe on jet streams. All over the planet, the sun's light and heat was blocked, a veil seeming to cover the sky. Global temperature dropped by 3 degrees Celsius. Crops failed, and over the following year, disease and famine killed as many as 80,000 people. As far away as Europe, snow fell in June, and 1816 became known as the year without a summer, the climate-altering blanket immortalized in the dramatically coloured sunsets of Turner's romantic landscapes. The Tambora eruption of 1815 was the largest and most destructive volcanic eruption in recorded history. Its effects were catastrophic not only to humans, but to the local ecosystem and global climate too. Natural catastrophes like this are an inevitable consequence of the global process of plate tectonics. But plate tectonics itself is shrouded in mystery. What powers it? When did it start? And how important really is it? It turns out, in the years following this brutal eruption, scientists discovered that as terrible and destructive as its consequences may be, plate tectonics could be the key to keeping Earth alive. At the time of the Great Tambora eruption, geologists were still striving to understand how the surface of our planet really worked. What created its mountains and ocean basins? What caused the natural disasters? If not the wrath of the gods? The belief was that the surface of the earth was a single, solid shell of rock. Yet nonetheless, there were clues hinting at colossal, invisible processes that shaped that shell. In the 16th century, it was Dutch cartographers who first noticed the curious shapes of our continents, shaped in such a way as to fit together like pieces of a jigsaw puzzle, despite being separated by great swathes of ocean. Assuming they were once joined, how did these great fragments of rock become separated? The favoured theory of the time was that of thermal cycles. Occasionally, scientists reasoned the Earth heated up, and as warm objects tend to expand, so the Earth expanded, cracking the crust and separating the continents. But in 1915, Alfred Wegener, a German meteorologist, proposed a new theory. Instead of thermal cycles separating continents, land masses wandered around the Earth like immense icebreaker ships ploughing through the Arctic basins. Wegener's ideas were groundbreaking and supported by a slew of new evidence. Not only the previously seen jigsaw of coastlines, but also the discovery of fossils of similar creatures found on continents oceans away. Indeed, when Robert Scott had made his doomed expedition to the Arctic several years earlier, he and his men had found the fossils of tropical rainforest beneath tundra and frozen rock. It was clear that the continents had not only been separated, but had also drifted from the equator to the poles. Fittingly, Wegener's theory became known as continental drift. But there was a problem. Despite the evidence that it had indeed happened, Wegener offered no explanation of how it came about. What forces could move entire continents? And how did they make their way through the solid rock of the ocean floor without breaking themselves up in the process? Eventually, Wegener's ideas of continental drift lost favour, but a seed had been sown for an entirely new theory, one which took the cutting edge of 20th century geophysics to realise. In the 1960s, a global network of seismometers was established for the first time, capable of pinpointing the epicenters of deadly earthquakes. And they revealed something surprising. Earthquakes didn't happen randomly all over the Earth's surface, but were confined to narrow strips crisscrossing the globe. Sometimes these strips followed the edges of continents, and sometimes they cut right through the centres of the oceans. Together, these earthquake-prone areas defined the boundaries of more stable slabs of rock. Those slabs are what we now know as plates, with the earthquakes concentrated at plate boundaries where they grind and crash against one another. New techniques to find the ages of rocks and the orientation of their formation added data to this new understanding of plates, revealing how they shifted and changed over time. And before long, a new thesis emerged with elements of the ideas that had gone before. The theory of plate tectonics was born. The concept is a deceptively simple one. The rocks of the crust have lost some of their heavier minerals, so they're less dense than the mantle underneath. So they float on top like rafts of ice on an Arctic lake. Continental rocks even more processed than those in the oceans, and therefore even more buoyant. They can build up to huge heights and still stay afloat, like towering icebergs. So, the surface of the Earth is covered with these rock rafts, bumping and jostling for dominance. But they do more than that. The plates are constantly moving, shifting, transforming. Where two plates separate, magma rises to fill the gap, hardening to create brand new rock, adding to the diverging plates on either side of the boundary. But growth of the plate can't go unchecked. Where the two plates meet and press against each other, the rocks can crumple, folding and breaking them into tortured, gargantuan heaps, like the Himalayas, the highest peaks of our world. But eventually, one plate triumphs in this planetary struggle. It's density that decides the winner, as one rock raft will inevitably be marginally more buoyant than another. The lighter rocks stand their ground at the surface, while the heavier crust is forced down, bending, subducting into the mantle. As the heavier rock descends, it's heated and melts, releasing its minerals and water. That melt creates huge volumes of magma, enough to feed explosive volcanoes, like mighty Mount Tambora. As geologists study the surface of the planet in ever more detail, all evidence seems to point to this slow war of growth and destruction taking place over geological timescales. But it's still not clear what powers this movement. Just as Wegener couldn't explain how continental drift worked, scientists today are still struggling to pinpoint the mechanisms driving plate tectonics and how they got started. And the constant recycling of rock means that, by its very nature, the process of plate tectonics masks its own history. The core of our world is immensely hot, a remnant of its violent formation and the decay of radioactive elements in the centre. That core is like a hot plate beneath a pot of water, delivering its heat into the fluid rock above. Warmer mantles rise, spread out, cool, and sink back down, creating huge sideways currents beneath the crust, pushing it along. But to truly understand what powers plate tectonics, we need to look back to its very beginnings. When the Earth formed some 4.5 billion years ago, and in the early Hadean eon that followed, nothing like modern plate tectonics could have existed. The rocks were too hot, too thoroughly mixed by the convulsions of the still forming, battered Earth. The outer surface of the planet froze into a single, solid shell, while the interior remained hot and molten. So instead of plate tectonics, a very different regime must have reigned. Although the crust remained stubbornly on the surface, the heat from the mantle still strove to escape. It warmed the base of that crust, and it became hotter and hotter until that solid shell began to melt at its base. Gradually, this molten rock dripped down into the mantle. There it collects and is superheated until it's hot enough, with little enough density, to come back up. Plumes of magma rising up through the mantle, punching through the crust, forging the very first volcanoes. So instead of the circulating currents of modern-day plate tectonics, the early motion was almost entirely vertical, up and down, rather than what we have today. Though vertical plumes are still somewhat seen in our present, the Hawaiian Islands form part of a chain of volcanoes formed by a plume of magma that has remained in place for 18 million years. But plate tectonics is now much more dominant than this plume volcanism. So at some point in the last 4 billion years, the Earth's tectonic regime transformed. How it happened, however, is still something of a mystery. Scientists' best guess is that as the Earth cooled, the compositions and temperatures of the mantle and crust gradually changed. The crust became weaker, fragmenting into small rafts, the precursor to the modern plates. If the edge of one plate dipped below another, subduction could begin, dragging the rest of the raft after it. With the advent of subduction, the heat transfer in the mantle was given a horizontal component for the first time. Convection currents were established, which helped the sideways movement of plates, making the process self-sustaining. Plate tectonics was born. Though we might take it for granted, it seems like this ongoing tectonic process is actually very rare in the cosmos. And we may have it to thank for our very existence on the Earth, for life itself. Other nearby planets might have geological activity, volcanoes and earthquakes, but their surfaces aren't being recycled by plate tectonics, and other nearby planets are, as far as we know, devoid of life. Perhaps it's not such a coincidence that both life and plate tectonics are unique phenomena to our world. Because the cycling of rock through the Earth's surface also has an important impact on another cycle, critical to life, the carbon cycle. Life is made of organic carbon compounds, but it also relies on inorganic carbon compounds like carbon dioxide to keep the planet's temperature at a habitable level, trapping the heat of the sun within the atmosphere like an insulating blanket. And carbon dioxide is expelled from volcanoes when they erupt. Extra carbon dioxide pumped into the atmosphere thickens the warming blanket and increases global temperatures. But some of the carbon dioxide in the air dissolves in the water droplets of clouds, and before long rains out into rivers, lakes and oceans all over the globe. There it reacts with rocks, breaking them down and making new ones, carbonates like limestone and chalk. Much of the carbon dioxide spewed out by volcanoes ends up trapped again, locked up in the sedimentary rocks of the Earth's crust. But plate tectonics hasn't finished with this carbon store. As the plates are consumed at converging boundaries, the sedimentary rocks are also subducted. They melt and release carbon dioxide back into the magma to erupt from volcanoes once again. In this way, carbon dioxide levels in the atmosphere reach an equilibrium, providing an environment that's not too hot and not too cold for life to thrive. Without it, we could easily end up like one of our barren, inhospitable planetary neighbours. A dead world floating through the void. Venus, with plenty of volcanoes but no tectonic recycling, witnessed the uncontrollable release of carbon dioxide into the atmosphere early in its existence. Some was locked away, but when no further reactions could take place, levels of the greenhouse gas continued to build. Oceans evaporated, and the rocks themselves altered to release carbon back into the atmosphere. Runaway heating led to Venus becoming the hottest planet in our solar system, its surface more than 450 degrees Celsius. Without plate tectonics, the planet baked to death. Mars, on the other hand, suffered a different but equally terminal fate. The red planet is smaller than the Earth, so cooled quicker. There's evidence for volcanic activity on the surface, but this has slowed as the planet aged. Less and less carbon dioxide was released into its atmosphere, and what was already there was gradually locked away in its rocks or blown away by the solar winds. Without a way to recycle the carbon stores, Mars was stripped of its insulating blanket and left out in the cold. Without plate tectonics, the planet froze to death. So, the recycling of carbon through the Earth's surface helped to maintain a temperature just right for life to get started and thrive. And plate tectonics probably offered other benefits to a young Earth and its tentative first life forms too. The twisting and shifting of plates across the Earth's surface created diverse environments and niches for life to exploit. Among these were hydrothermal vents, which form around the diverging boundaries in the middle of oceans. It was around vents like these that our last common ancestor found refuge while the Earth was bombarded with meteors in the early Archean. So, even though volcanic events like the catastrophic 1815 eruption of Mount Tambora have the capacity to wreak havoc on local ecosystems and global climate, they are an essential part of a wider process that is keeping our planet alive. In this way, plate tectonics could just be the key to making a planet habitable. Next time, we'll investigate an altogether more alien explanation for life on Earth. We'll look at the earliest fossils ever found on our world, and we'll investigate what could have happened had life never evolved on our planet. You've been watching the entire history of the Earth. Don't forget to like and subscribe and follow us on Instagram to keep up to date with the amazing artwork produced for the show. And we'll see you next time.